So we are now on diffusion concerning liquids. So we're done with gases. We're now go to liquids, and then we will have solids. Now, diffusion of solutes in liquids is actually very important in many industrial processes. Now, especially in such separation processes that I have discussed with you during the intro, some of which are liquid-liquid extraction or otherwise known as solvent extraction. I've also given an overview of the gas absorption and even distillation. So this particular processes involves diffusion in the liquid phases. Now, diffusion in liquids also occur in many situations, even in the natural observable phenomena in nature, such as example stated in your unit operations by John Cooklis is the oxygenation of our bodies of water, such as lakes and rivers. And even in our bodies, physical bodies, we have diffusion in liquids illustrated and manifested in the diffusion of salts in the blood. So there's a need for us to understand it fully now, applying it in unit operation processes. So the first part that we're going to discuss regarding diffusion in liquids is equimolar counter diffusion. I have in part shared with you this formula last meeting, and the first formula gives you the flux, Na, of solute A that is, and the unit of such is kilomole A per second per square meter. And again, you have the appearance of the molar diffusivity of A and B in meter squared per second, and you have the concentration of A at 0.1, which is Ca1 in kilomole per cubic meter, and you have the mole fraction also appearing in the formula in the second part here of A at 0.1 as XA1. So if it's a 0.2, then that would be XA2. Again, your Z2 minus Z1 here is the diffusion distance, the distance in which solute A is going to diffuse to another, let's say, liquid phase, which is in B. We will label in B. Now, in this formula, you have the appearance of the C sub AV, and that's given or defined again by another formula. So before you can process the one on top, you need to process this first. So this needs your densities, density at 0.1 and density at 0.2 for both A and B. And that is, I'm referring already to the mixture of A and B, because in here we're taking the average total concentration of A and B in kilomole per cubic meter. And in such also, we're getting the average molecular weights of A and B, mixture of A and B at 0.1 and 0.2, so that we'll be able to substitute it in here. As for the densities, then they will also be average densities at 0.1 and 0.2. Now, as for diffusion of A through non-diffusing B, so this one is in the case wherein there is equal amounts of A and B diffusing in both direction, counter diffusion. So meaning if A is going to the right, B is going to the left, or the direction is counter to that of A. And it's equivalent. So it says equimolar counter diffusion. In here, we have the diffusion of A through a non-diffusing B. Most of the time, this B, if it's non-diffusing, it's stagnant B, non-moving. So A is, in this case, we understand that A is going to diffuse to B, but B will not diffuse on A. So our flux in this equation is given by this formula, which has a new addition of this particular variable x sub B m. Now, x sub Bm actually is the mole fraction of B, but this time it's the log mean of that mole fraction, because we're not simply getting the mole fraction of B at points 1 and 2, but we're making use of the ln in the denominator. That way, we are determining the log mean of the mole fraction of B at points 1 and 2. So after you've taken the value of x sub Bm, then you go back to the original formula and substitute. Now, for dilute solutions, this particular equation that we have on top will be simplified in this form without any more the appearance of the x sub bm. Now, if you will read on, complement my discussion here to what is written in Janko, please, because all of the sample problems given here are taken from our uh, major reference book, Jan Kuplis, but the current edition, the Philippine edition. If your solution is dilute, this x sub bm is more or less equal to 1. So that is why in here, in the formula that you are seeing here below, you don't see it anymore. It's equivalent to 1 if solution is dilute. So it says here dilute solution. Now, so we have this sample problem of ethanol. Let's say ethanol is our solute A diffusing to the non-diffusing B. So, and they have this particular solution. Now, the film is 2 mm referring to the B. So an ethanol water solution in the form of a stagnant film 2.0 mm thick. So the film consisting of A and B, solution of A and B is this thick, 2 mm thick, is at 293 Kelvin and is in contact at one surface with an organic solvent in which ethanol is soluble and water is insoluble. So in this particular scenario, in the first statement, only ethanol will diffuse to your organic solvent. And then your water is not to diffuse. This is the non-diffusing component that we're referring to in the second or in the previous slide. So in this case, the flux of B, since it's non-diffusing, only A is going to diffuse through our organic solvent, then it would be equal to 0. At point 1, the concentration of ethanol is given to be 16.8 weight%, and the solution density is 972.8 kilogram per cubic meter. Now at point 2, the concentration of ethanol is 6.8 weight%, the other one is 16.8, and with a density of 988.1 kilogram per cubic meter. You're given the diffusivity of ethanol to be 0.740 times 10 raised to negative 9 meters squared per second. And we are after here the steady flux of A, and that is of ethanol, or the steady state, specifically the steady state flux of ethanol. So we're going to write the solution to this problem. I'm going to share my board to you now. I can see my board rate class. Okay, so if we will directly go to the substitution or the solution of this problem, we will not anymore go to the given. Anyway, you can read them again and access them again if you even have a soft copy of John Q, please. So if it's the flux that is being required, calculate the steady state flux of A, then we need the starting point of our solution always is with the formula that will guide us as to what things we need to determine. So for that rate in which A is going to diffuse to our solvent, organic solvent, it's given by the formula that I have shown to you in the slide, but I will write it in here. I will not anymore change the sharing. And okay, this is our formula for the rate in which A is going to diffuse to be in kilomole per second per meter if we will have those units. But it's always mole per unit time per unit area, XA2. XA1 minus XA2. So then we can determine based on this formula what we have in terms of the information that we can use and what we still don't have. Now the problem gives us the diffusivity. So we have this already. As for the average concentration, we don't have it yet. As for the Z sub 1 minus C sub 2, it is stated in the first statement that the film is 2 mm thick. So it's 2 mm thick. So that gives us already this 2. The Z sub 2 minus C sub 1 as a whole. So we have this 2 already, the difference of the 2. Then we need as well the mole fraction of A and the mole fraction at point 1 and the mole fraction of A at point 2. So these three we still do not know. So we will label this for now as our equation 1. We can't solve anything for now. So we need to determine the things that would lead us to the NA, the flux that is being asked in the problem. Now, for us to be able to determine the, by the way, class, I think I missed something writing here. I think I missed in the formula the X sub Bm. This is the lube mean mole fraction of B, and that is referring to water at points 1 and 2. So I'm miswriting this one. And this one we also do not know. Now, based on the slide that I have shown to you, I'd like to go back to the slide so you will see. Sorry, class, that's still the second slide. We are given this formula of X sub Bm. In the numerator, we have the difference of the two mole fractions of B, 0.2 and 0.1, then the ln at the denominator. So we will use this formula in determining the X sub Bm that we have as unknown in the formula in here. So we don't have it. We don't have this, and we even don't have these two as well. But if we know your XB2 and XB1 in here, your XA1 and your XA2 will just follow because the sum of the two will always be equal to 1. So I'd like to go back to our board. So I'd like to solve first your XA1. Your XA1 is mole fraction. The problem, on the other hand, give us, I'd like to read the problem. At point 1, the concentration of ethanol is 16.8 weight percent. So this is weight percent, and it has to be converted to mole percent. So I'd like to write here the percentage in terms of weight. So 16.8, this is weight percent A. Now, if we'll say we'll have a 100 kilogram or 100 gram solution of A and B, then the mass of A is 16.8 grams. So we will use that in determining the mole fraction of A in the solution of A and B. So you will have a 16.8 grams of A in a 100 gram solution of A and B. And to convert this to moles, we need to divide it by the molecular weight of ethanol, because ethanol is our A. So our molecular weight for ethanol is 46.05. I will have here written molecular weight of A is equal to 46. Yes?
Why ka mas naka-share screen?
Why ako naka-share screen? Why are the rest silent? Anyway, okay. Now, I'll write here as well the molecular weight of B. And in this case, our B is water, so we'll write it as 18. Now, if I have a 16.8 here divided by 46.05, this is just representing the moles of ethanol. I will need to add to it the moles of water. And if I have again a 100-gram solution of A and B, then 100 minus 16.8 would be 93.2. And we'll divide this by 18. Now you have converted the percentage by weight to mole percent. So in this case, your moles of ethanol now will be, will you check, 0.0732, 0.0732. This is at point 1. So if you need to determine point 2, the same principle applies. So this time, you will have to use the weight percent of B. So the weight percent of B is, at point B rather, is 6.8. So we have 6.8 weight percent of A. This is at point 1. And this is it, point 2. Okay, we need to get the mole fraction of A at point 1 and point 2. Now we need to have here 6.8. We divide by 46.05. Then in here we have 6.8 divided by 46.05. And again, we subtract the 6.8 from 100. It will have a 100-gram mass of A and B. So this would be 93.2, right? 93.2, and we divide this by 18. This represents the mole of water. Moles of water, this represents the mole of ethanol. And we will be getting here a mole fraction of water, of ethanol rather, in point 2, which is 0.0277. This is for still ethanol at this time at point 2. It's mole percent. Now, if you know, so now we know already these two. We know already these two. Then for us to be able to get XBM, we need to, excuse me class. Pwede gani. So you have to subtract only XA1 and XA2 from 1. So you will have 1 minus XA1 will be equal to, so that would be your XB1. So your XB1 in this case is 0.9268. Now 1 minus XA2 will be your XB2, and that would be 0.9723. So now if I know XB1 and XB2, I can determine my XBM. So we will determine our XBM. And I have shown to you the formula a while ago. So XB2 minus XB1, the ln of XB2 over XB1. And it would be just substitution. So you get the values here of 0.9723 minus, so your XB1 is 0.9268. And you'll have the ln of 0.9723 divided by 0.9268. So you will have the log mean of the mole fraction of B in points 1 and point 2 being equal to, you just check, I'm getting this from the book, so 0.949. Now, if we go back to our formula, the only thing that remains now is, so we know already XBM, so the only remaining value to determine is the XAB, and that's the average concentration of the solution of A and B. So that's the next thing that we will determine, CAB. So you have your C sub AB being equal to, so in this case, you need to get the densities, density 1, density 2, M1, and M2. Now I'll write density 1, M1. I have shown the formula to you a while ago. So this is how we get the average concentration. So I need the densities. I think in this case, the problem gives us the density. Uh, The problem gives us the density, so we need not worry about density 1 or the density at point 1 and the density at point 2. Now we need to determine the molecular weights, the average molecular weights at point 1 and point 2. If it's the average molecular weight, we know that molecular weight is mass over the moles, and it will go back to our original assumption of the mass of our solutions here. So we have assumed that we have 100-gram mass of solutions of A and B. So what I'm going to do for density, for M1, I will have a 100-gram mass at point 1. So this is mass, so I need the moles. So for me to know the moles at point 1, I'll go back to what I have here, the moles of A and the moles of B at point 1. So the moles of A at point 1 is, can you please solve this one? I don't have a value to refer this to in here. So we have a 16.8 divided by 46.05. So your moles of A at point 1 will be 0.3648. The next question is, what would be the moles of A at point 2? Moles of A at point 2, because this one is our average molecular weight at point 1. By the way, class, this is mass and I need the moles of A and B. This 100, by the way, I stand corrected, is the mass of A and B. So your denominator has to be the total moles of the solution consisting of A and B. And since this is already moles A, then you should need to find the moles of B. So in this case now, how do we find the moles of B in this case? How do you find the moles of B? Anybody? How do you find the moles of B at point 1? I have here the data that you can use. How do you find the moles of B at point 1? Ara naman lang bida siya ho. How do you find the moles of B at point 1? I already took the moles of A at point 1. What's the moles of B at point 1? That would be, okay, so that would be 93.2 divided by 18. This is your moles of A. This is your moles of B, all at point 1. So I'm getting it from the denominator that I'm showing to you. So it's 5.7, 5.18. So I will have here 5.18. You do the same thing, you will have an answer here, and you do the same thing for M2. The total mass of A and B at point 2 would still be 100, but this time I'm going to get the moles at point 2. So for A, that would be 6.8 divided by 46.05. So that would be a 0.1477. A 0.1477 here. And for B, 0.2. So this is 0.2 and this is our B. 93.2 divided by 18. That should be 5.178. So this is 5.178. And you will have the value of M2 and M1 now. In the first here, you will have 100 and you divide it by the sum of 0.3648 and 5.18. This should give you an 18.035. The other one is 100 divided by 0.1477 plus 5.178. And that should be 18.777. Now you have already the two molecular weights, then you can go back to the formula that we have for the average concentration. So the density at 0.1, I will just get it from here, is 972. This is 972.8 kilogram per cubic meter. Then your M here should be in kilogram per kilomole. So in this case, you have 18.035. This is kilogram per kilogram mole or kilomole. So that cancels the kilogram. Then for the second density, the density at 0.2, that would be 988.1, and having the unit again, set of units, kilogram per cubic meter, which we will divide by this, the 18.777 kilogram per kilogram mole. Then we have division by 2. So our resulting unit will be a concentration in kilomole per cubic meter. So I'll write it here. So in this case, you have a 972.8, which we need to divide by 18.035. We add to that the quotient of 988.1 divided by 18.777, and we divide by 2. So our average concentration in kilomole per cubic meter is 53. So this is 53.28. So having the unit of kilogram mole or kilomole per cubic meter. Now we have the CAV. That's the only thing that remains here to be determined. So we have it here. So now we can substitute for the flux of A. So we have NA is equal to DAB, and we have CAB, Ca molar volume, by the way. So this particular concentration is known as molar volume. It should be V as in victory. So V A V. Okay, our denominator will have XBM. Then we have Z2 minus Z1. Then we have your XA1 minus XA2. Let me check if I have everything correct. So our formula, now that we have everything there, then we just substitute. So our DAB, the problem gives us a DAB, a diffusivity of ethanol of, a molar diffusivity of ethanol of 0.740, correct, times 10 raised to negative 9, and this is meters squared per second. The CAV that we got a while ago is 53.28. So this is kilomole per cubic meter. Then we'll just as well place in here the XA1 and the XA2. 0.0732 minus 0.277. So this is na moles of A over mole of solution. Then XBM, our XBM is 0.949. And we need the, and this is by the way kilomole as well. It's kilomole per, the denominator does not have any unit because it's log mean concentration of B. Then our diffusion path of length 2 mm. So your 2 mm should be converted in meters. So 2.0 times 10 raised to negative 3 meters. This will result to a flux of, so if we will compute, we multiply the D sub AB to the molar concentration or molar volume. Then we have 0.7032 minus 0.0277, and we divide by 0.949, and we divide by 2.0 raised to negative 3. So our answer is, wait, my answer is wrong. 0.740 exponent times 10 raised to negative 9 times 53.28 times 0.0732 minus 0.0277 divided by 2 exponent negative 3 times 10 raised to negative 3 divided by 0.949. So that would be 9. So in this case, it's 9.45 times 10 raised to negative 7. I think the difference here is the answer that is given in the book for the concentration, the molar concentration here. Maybe I got it wrong here. My answer is 53. While in the book, it's just 50. So 972 divided by, wait, why is this 20? The M1 is 20. So 100 divided by moles of A plus moles of B. Wait, class, I did not got it correctly. We'll have 16.8, we divide by 46.05. It's correct, 0.36. That's moles A, 0.36 for 40. This is 40. And this is, okay. What about moles of B? That would be 100 minus 16.8. So that's, oh, you did not correct me. 100 minus 16.8 is 83.2. So everything here is affected. So this is 83.2. This is 83.2. So this will change. So this will change. Your 16.8 divided by 46.05 plus 83.2 divided by 18 This will be your denominator. And we will multiply it again by 16.8 and divide by 46.5.